Welcome to Math 31. In this lesson, we are beginning Chapter 2, which looks at derivatives. And derivatives are really important in calculus, and this is really where we start getting into calculus. The work that we did looking at limits up till now is typically referred to as pre-calculus. It's just setting the stage for understanding what's going on in calculus. So here we begin with a definition. Now, a little bit odd, it seems sometimes. When we look at definitions in math, it can come without any words. So here we're told that given a function f of x, the derivative is defined as this limit. This is the definition of a derivative. And as you look at this limit, it probably looks familiar. We have the limit as h approaches 0 of f of x plus h. Now that's different. Here we're keeping the variable x, there we go, in the formula, but we looked at this, we called this formula 2 back in chapter 1, where we had an a or a number in place of these x's. But now what we're doing is we're finding a function. So here I have a function that depends on x with this little symbol there. So this symbol tells me it's a derivative as distinct from this function that we have over here, just f of x. So we call this f prime of x. And so we'd say, let's see, I have that right down here. This is read f prime of x, or the derivative of f with respect to x. So what happens when we find this limit is we get some function where x is our independent variable. So just like the function f of x, the derivative f prime of x is a function that depends on the variable x. Well, this definition didn't have any words in it. So this next line gives us some words to help us understand. So the derivative defines the slope of the line that's tangent to the function. So it defines the slope as a function of x. So f prime of x, this is a function that tells me the slope of this function for any x variable, x value that we choose. So for example, as we come over here, the slope of the tangent line to the function f of x at the point where x is equal to 3 is f prime of 3. So I just plug the number into this derivative function, and that gives me the slope at this x value of 3. Well, that should be pretty familiar, actually, based on the work that we did in chapter 1. Now we're just formalizing it as we get into this in chapter 2. The domain of the derivative is the set of all values of x for which the limit exists. What limit? This limit up here. Okay, so wherever this limit exists, the derivative exists as well. And so that means we need a left and right hand limit that would be equal to each other. That's one way we test if a limit exists. Next point, the domain of the derivative, f prime of x, is always a subset of the domain of the original function. It may include the entire domain, or it could be less than the entire domain, but it can't extend beyond the domain of our original function because you can't find a slope to a function somewhere that the function doesn't exist. So we'd say that the derivative is always its domain, always a subset of the domain of the original function that we're looking at. All right, here's some other notations for a derivative. And one reason why we have other notations is because this work of figuring out this idea of derivative of a function that would describe the slope of a curve, of the tangent line to the curve, it was kind of being developed at different places in the world around the same time, and different notations were used. So we had that f prime of x. We could just write it as y prime. here we have the f prime of x. But there's also this other notation which looks like dy over dx. Now for now, don't think of this as a fraction. Think of this as the derivative of y with respect to the variable x. Later on in the course, hopefully we'll talk about how we could break this into pieces and think of it as two parts, but it's not at all helpful for us at this point. So best for us to think this means the derivative of y with respect to x. Over here, this says the derivative with respect to x of the function f of x. So all four of these notations are saying the same thing. All of them are saying we're finding a derivative function for whatever this function is, y equals f of x. And so here we have that in words. Dy dx means the derivative of y with respect to x. So let's look at an example. We want to find the derivative of each of the functions that we're going to look at next. First one I will work through with you. The second one will make it check your understanding. So we want to find the derivative of this function. Well, how do we do it? We go back to the definition of a derivative, which is this limit. So I want to find this limit, and that will give me the derivative function. Well, we did this a fair bit in chapter 1, so let me just slide these steps out here. So the limit of f of x plus h, so I replaced the x up here with an x plus h, and then I still have the minus 3. So this first radical is f of x plus h minus f of x, the second radical, all over h, and I'm finding the limit as h approaches 0. As we dealt with this type of question in chapter 1, we need to use conjugates, because if I simply plug in 0 for h, I have the root of x minus 3 minus the root of x minus 3, 0 over 0, problem. So we need to rationalize our numerator. And we do that with a conjugate. Again, remember, when we're looking at a conjugate, if the sign here, let's make this yellow, is a subtraction sign, then its conjugate has an addition sign between our radicals there. Well, when we multiply out that numerator, the radicals will disappear. And this is what we get without the radicals. In the denominator, again, I didn't bother expanding because my goal was to do some simplifying to the numerator. And that has been done. And then once I've done that, then I can look and see, well, how can I simplify this? Well, here I have an x minus an x. They cancel out. And here I have a negative 3 minus a negative 3. They cancel out. So all that I'm left with, pardon me, in my numerator is this h. And that's what we'll see in the next line here. Oh, I even showed distributing. There we go. I made it simple for us. And at this point, we can see what's canceling out. My positive x, negative 3, positive 3. Only the h is left over. And that h should cancel out with the h that's in the denominator. As I can show in the next line here, this h, that h cancel out. Remember, we don't have nothing in the numerator. We still have this 1 that used to be an invisible coefficient, but now we can see it. And when they cancel out, I will get this when I substitute 0 in place of the h that is left over. So this h is approaching 0, and so that's what I've shown here. If that goes to 0, then I have the square root of x minus 3 plus the square root of x minus 3 in my denominators, giving me my derivative function, which is 1 over 2 times the square root of x minus 3. Now here I put this domain here on the derivative function because we were asked that in the question. I kind of skipped past it. But you'll see up here it says state the domain of both the function and its derivative. Well, I skipped this original function. Here, I can't square root in negative, and so my x value has to be greater than or equal to 3. But notice here, my derivative function, now my denominator can't be 0. So if x was equal to 3, then I'd have 3 minus 3, 0 in the denominator, not possible. So we can see that this domain is a subset of this domain. Okay, not quite exactly the same. And essentially what we're saying is that here at the very end of this graph, this derivative is not defined, which means I can't find a slope at that endpoint on the graph. On the next page, you will see another function. And let's make this check your understanding. So I would like you to find the derivative function. Well, let me just come back to this one for a moment because I don't think I mentioned what does it mean. So suppose I wanted to find the slope of this function where x was equal to 4. I'd plug a 4 in here, that would give me the y coordinate. But here, if I plugged a 4 in at this point, that would tell me what is the slope of this function where x is equal to 4. Okay, now why don't you have a look at this question? And again, we want to find the derivative, so we want to go back to the definition of the derivative. Even though it has g of x's, I'm going to use that definition with g of x's here, work through this question, restart the video once you have finished this question. Okay, you can pause now. Well, here's my process. So first of all, I'm going to replace all the x's with x plus h initially in my function, and then subtract when I just leave them as x's. Since I have a fraction over a fraction, or rational expression on the top, I want to get rid of those denominators. So I'm going to multiply everything on top and bottom by that common denominator, the x plus 5 times x plus h plus 5. When I do that, here's what I get once I do that expansion. So I haven't shown all the details there, but when I take this deep red part and I multiply it to this first expression, the x plus h plus 5's cancel out, and I have an x plus h times an x plus 5 times the 2. So that's where these first 4 terms are coming from. And then secondly, when I multiply this pair of factors to this second expression, the x plus 5's cancel out, and I have this negative 2x times x plus h plus 5. That's where these 3 terms here are coming from. Once we get all that expanded out, then I can start looking to see what I can cancel out. And again, what I'm expecting is all 3 of these terms should be canceling out. So let's start with this one, negative 2x squared. Well, negative 2x squared, positive 2x squared, they're gone. Then here I have a minus 2hx. I look over here and I have a plus 2hx. Those terms cancel out. And here I have a minus 10x. And here I have a positive 10x. This cancels. With that, all I'm left with in the numerator, watching the sign, it is a positive, that's good, is a 10h. Does this work? Nope. Well, let's pull this out. So there we go. We have the 10h on top. And again, my denominator, I didn't expand out, kept it in factored form. And at this point, I can see that as h goes to 0, these two h's can cancel out. And I've gotten rid of the 0 over 0 problem. And now this h can approach 0. So my numerator will have a 10. My denominator will have an x plus 5 times an x plus 5. Giving us this function, 10 over x plus 5 all squared. Now, one thing that we haven't done yet is I didn't look at the domains for each of these. So as I look at my original, and what color will we pick? Let's go with just black. Here, this denominator can't equal 0, which means x cannot equal negative 5. So my domain, all real numbers except x cannot equal negative 5. Down here, it's the same thing, that x cannot equal negative 5. So my domains are identical, and that's okay. Now, on the previous page, we said the domain of the derivative function is a subset of the original. Well, this domain is entirely within this domain up here, so it fits the definition of subset, even though it's exactly the same. So two sets that are exactly the same, we can say are subsets of each other, and that's okay. All right. Let's talk about another definition, and this is the definition of differentiable. So here we'd say a function is differentiable at the point where x is equal to a if this derivative exists at x equals a. Okay, so this part is important. So we'd say it's differentiable at x equals a if this limit exists wherever x is equal to a. So maybe I should add that at the end here, where x equals a. In other words, it's going to be within the domain of this derivative function. So here we have some, in other words, explanation to help us. And as I read through this earlier, it's a little bit redundant, but that's okay. So it's differentiable if the function is continuous for x equals a. And then I said the left and right hand limits approach the same value. Well, that has to be true in order for the function to be continuous. But it's helpful for us to think of the left-hand slope and the right-hand slope approach the same value as x approaches a. And then the slope of the tangent line is finite number. So we don't have a vertical tangent line. So I guess this isn't quite redundant. This is a different statement here. The left-hand slope and the right-hand slope approach the same value. Well, let's use these three ideas as we look at this next example. So we're going to look at this a value for these 5 different functions, and we want to state, is our function continuous, and then is it differentiable where x is equal to a? So we're not worried about other points, only where we have those dotted lines. So as I look at this curve here, is the function continuous? Well, for the function, my left-hand limit is approaching this number, my right-hand limit approaching the same number. How's my function defined? Well, it's defined at that same point, so we'd say, yes, this function is continuous. Is it differentiable? So we have met that continuity condition. If we had to say no here, then we'd say, well, it can't be differentiable if it's not continuous. So let's kind of look ahead here, and we'd say, oh, this one, it's not continuous at x equals a. If it's not continuous, it cannot be differentiable. Similarly for this one, it's discontinuous at x equals a, not continuous, which means it cannot be differentiable. All these others, so this one is continuous at x equals a, this one's also continuous where x equals a. So that's dealing with this first condition for whether a function is differentiable. By differentiable, we mean we can find a derivative. We can find a slope of the tangent line. Now let's look at these next 2 bullets. As I look along here, I can see that the slope, let's say at this point, the slope of my tangent line goes up like this. Here, the slope of my tangent line kind of goes like that. That's pretty ugly. My tangent line is approaching, I should say my tangent line approaches this as I come from the left side. As I come from the right side, this is my tangent line, this is my tangent line, but it's approaching exactly the same tangent line. So we say it meets this second condition. The slope to the left of this point and the slope to the right of that point, both slopes are approaching this same tangent line. So it meets this second bullet condition. And at this point, our slope is a finite number. Looks like a negative 1-ish, I don't know, that neighborhood, but it's not infinite. So I don't have a vertical tangent line. So this, we'd say, is differentiable at x equals a. For this one, my slope on the left side, well, I have this constant slope all the way along, and as I get closer and closer to this point A, my slope stays at this positive 1-ish. As I look from the right side, I have this constant slope, and as I move closer and closer to this point A, it stays at a negative slope. So my slope from the left is positive, my slope from the right is negative. This condition here is failing. My left-hand slope and right-hand slope are not approaching the same value. So we'd say at this point A, my function's not differentiable. In other words, what is the slope of a tangent line at a point like this? Should my tangent line go like this? Should my tangent line go like that? Should it be more like this slope, more like that slope? We just can't tell at a point. So where we have a graph that comes to a point like this, we would say it's not differentiable at that sharp corner at the point. Well, let's jump over to the last one. As I look at my left and right hand slopes, so slope from the left side, here I have a gentle negative slope. As I go to the right, it becomes a steeper negative slope, steeper negative slope. At this point, it looks like my slope probably goes straight up and down. From the right side, same thing. I have this gentle negative, but it's getting steeper and steeper, and it looks like it comes to a vertical line here. So we're meeting this condition here that the left-hand slope and right-hand slope are approaching the same value. But we fail for this last bullet. Our slope is a vertical line. And a vertical line, we would say, is not differentiable. So we'd say this is not differentiable because, again, if we come back to this definition of a limit, if this is approaching either positive or negative infinity, then we'd say the limit doesn't exist, right? So if this limit doesn't exist, that means that the derivative also doesn't exist because it's not a finite number or a finite slope at that point. Okay, with that information, I'd like you to take a look at this next page. And here we have, I guess it's one check your understanding question. So what I'd like you to do is find the derivative. And so the function that's graphed is this f of x function. So find the derivative and then sketch a graph of the derivative on the same grid. And then we're going to look at the comparison between the two of them. So pause the video at this point, work through this check your understanding question, and restart once you've finished finding the equation for the derivative and also sketching the graph of that derivative. Well, here I've started the question. I have f of x plus h minus f of x all over the h, and then I expanded those terms out. I expanded this binomial cubed, and that gave me these first four terms. And right away, because I had this plus 1 minus this positive 1, I canceled those out right away. So they disappeared before I even got to my next line. Once I'm at my next line, I can see that from the expansion of x plus h all cubed, I had an x cubed minus the x cubed. Those cancel out. And so I have these three terms left. Each of those terms has an h in it. So I can factor out that common factor of h. And then these two common factors cancel out. Again, when I cancel out the h from the denominator, I still have a 1 down there, so it's not a 0. But then I have these two terms that had h's. Since I have h approaching 0, both of those terms go to 0. So what I get is my derivative function is equal to 3x squared. Well, 3x squared is a parabola, and you graphed parabolas back in grade 11. So we have a vertex at 0, 0, and a parabola that is opening up, and here are some points on that parabola. So this is what our graph looks like. Now, as we look at this graph, I want to look at the relationship between these two graphs. So let's see what we can look at here. Maybe I will start with a line. Let's go with a blue line. Suppose I look at this point here, and if I was to draw a tangent line at this point that's along the y-axis for my original function, I get a horizontal line. What is the slope of a horizontal line? Well, the slope is 0, which is why my y value for the derivative function is at 0. So what we're doing is we're saying the slope of this original cubic function is the y value on this red function. So let's look at a different point. Suppose I was to look at a point down here. As I look at that point and I think about, well, what is the slope at that point? Well, I'm going to take this line and I'm going to tilt it up a little bit to say, oh, what's my slope? Is it about that? Mm, let's see, my tangent line kind of looks like this. That's not bad. So there's the slope of my tangent line at this point. Is this slope positive or negative? It's a positive number, which is why on my derivative function, this y value up here is a positive number because this y value at this point is equal to the value of this slope at this point. And as I look to the left, I had a steeper slope, which means I had a larger slope, which means I have a larger y value. As I move to the right from here, my slope decreases and approaches 0 once I get to this point. So what that means here, my y value decreases and approaches 0 at this same point. But then as my cubic function continues to the right, from this 0, it increases to a slight positive, bigger positive, larger positive slope as I go up this way. So what happens on my derivative function? Well, my y value gets a little bigger and then a little bigger, and then it grows more and more so that these y values along this red curve match the slope values of the original cubic function. Well, let's look at some more examples. Here we have 4 different functions that were given, and we want to think about what does the graph of the derivative of these functions look like. Well, here we want to graph the derivative function given these original functions y equals f of x. And I've given you a hint there, similar to what we did in the previous question. The slope of the graph of the original function is the y value on the graph of the derivative function. Well, these graphs will be approximations, so they won't be exact. But there are a few points that we can plot exactly. And here's where I would start. I would look at this point here where we have a horizontal tangent line. And I would draw a dotted line down to here. And then same thing at this point, I have a horizontal tangent line. And so I'm going to draw a dotted line down here. Wherever I have a horizontal tangent line on my original function, that means that I have a slope that's equal to 0. So here, horizontal tangent line, slope is 0. Horizontal tangent line, slope is 0. Since my slopes are 0 at those 2 points, that means on my derivative function, so this will be f prime of x, on this derivative function, my y values equal 0. because the y values represent the slope of the functions. So as I look here to the left of this first maximum, I have a really steep slope here, so that's a large positive slope that decreases to 0. So that means I have a large positive y value that's going to decrease to 0. But then here my slope switches as it goes from positive to 0, then it goes negative, and then somewhere around here we reach the steepest point. So that's going to be the most negative slope, and then the slope increases back to 0. So kind of if I look directly down from here, I could do another dotted line, but I'm going to reach a minimum y value where I have my smallest slope, and then it's going to increase again to 0 because here my y values need to match my slopes. Negative y values to a minimum, and then increasing back to 0. Negative slopes to a minimum slope, and then a slope increases back to 0. And then my slope goes positive and then steeply positive. So my y value goes positive in that direction. So this is roughly what my derivative function would look like. Key points are these x-intercepts. As we look at our next graph, what we discovered is that a function like this where we have a corner or this sharp point, we know that it's not differentiable at this point. Let's get rid of those two little things and we'll draw this again. So again, I'm going to put a vertical line coming down here. This time, rather than being an x-intercept like we had over here, this is going to be where my derivative is undefined. But as I look at this, I have a constant negative slope, which means I have a constant negative y value. Well, I need to shuffle this over just a little bit this way. How far down is this y value? I don't know. I have no scale. I just know it's negative, so I'm going to approximate it. And then similarly over here, I have a constant positive slope, which means that I'm going to have a constant positive y value on my derivative function. And as I look at these two slopes, they're pretty similar in terms of their steepness. So I made these two a similar distance away from the x-axis. If my right side was much steeper going positive, then I would have used a larger y value up here compared to this y value down there. Now, one thing that I haven't drawn in is what's happening here along this dotted line. Well, we said it's not differentiable. So I have this line that's continuing to the right forever, continuing to the left forever, assuming that these graphs were also continuing. But at this point, it's not defined, so I'm going to do an open circle. Not defined here, so I'm going to do an open circle. So this is what my derivative function would look like given this graph. As we look at the next one, we also know that a graph is not differentiable where we have a vertical tangent line. So here, where we have that vertical tangent line, I can't find a derivative. So that's going to be a significant point on my graph. What's happening? Well, here I have a positive slope. So a positive slope that actually gets larger and larger and approaches infinity, approaches positive infinity. So here I have a positive y value that is increasing and approaching positive infinity, so this will be a vertical asymptote here. On my other side, I also have positive slopes, which means I need positive y values over here, but I'm starting with essentially an infinite slope. So I'm starting with an infinite y value, and then it's decreasing but staying positive. So my graph will kind of look like this. We don't know what's happening beyond that, so we don't know what's going to happen beyond the edges of this graph. Then let's look at our fourth graph. This time we have a cusp. So a cusp is different than a corner. again, that's going to be a point where our function's not differentiable, so I can't find a derivative, so I'll draw a dotted line down here. And again, the dotted line is just a guide. It's not a part of the derivative function. It just helps me sketch a better graph. What's happening with the cusp is, here I have a negative slope, negative, 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 and then it kind of swoops down, and what it's doing is it's approaching a slope of negative infinity. So I have a negative y value that's going to approach a negative infinity. So I'll have this vertical tangent line here. On this side, if I came from this side, I have a positive slope that becomes steeper the closer I get to this point. And actually this as well is going to approach a positive infinite slope. So my graph on this side comes from a y value of positive infinity, and then it's going to decrease, but going to stay a positive. So this is positive right to the edge. So I don't know if I like that. I think I'm going to make it swoop a little bit quicker because it looks like this is almost approaching linear, so almost approaching a constant y value. So I'm going to have this almost approaching a constant y value as well. Maybe that's a little bit too much. But the key thing, this is going to be a vertical asymptote. This was a positive slope, positive infinite. From this side, it was a negatively infinite slope. And that's how we get this shape of graph. Okay, as you look at the next page, I would like you to sketch what these three derivative functions would look like. Well, let me show you my graphs. Here's my first one. So here I had a constant slope of 0, which meant I needed a constant y value of 0. This middle part, I have a constant negative slope, so I have a constant negative y value. And then I have a constant positive slope, but it's relatively small compared to how steep this one was. So this positive y value needs to be closer to the x-axis than this y value down here was. So this needed to be further away from, I should say, the x-axis than this one was. Okay, and those are the graphs I get for number 6. Well, for the first one in number 6. Here's what I'm getting for my second graph. So at these 3 points, we had a horizontal tangent line. And so wherever we had a horizontal tangent line there, and there, I need zeros because the slope is 0, slope is 0, slope is 0, y value 0, y value 0, y value 0. All right, here I have a negative slope approaching 0 and then going positive, which means I have a negative y value approaching 0 and going to a positive y value. I reach a steepest or largest slope around here somewhere, so I reach a largest y value around here. And then my slope decreases back to 0 and goes negative. So my y value decreases back to 0 and goes negative until I reach a minimum. So my steepest negative slope is my smallest y value, which is around here. And then it increases again to 0. My slope increases to 0 and then goes positive. So my y value increases to 0 and goes positive. The last graph. Again, we have a cusp. So I'm going to look at the cusp, but I'm also going to look where my function had some horizontal tangent lines. So I did have a horizontal tangent here and a horizontal tangent there, which meant I had zeros for the y values. My cusp, here I had a positive slope to 0 to negative, positive y value to 0 to negative, but my slope is decreasing, approaching a negative infinity, so my y value is approaching a negative infinity. From the other side, here I have my slope of 0. To the left, I have a positive slope that approaches positive infinity, so my y value is 0, positive y value is approaching positive infinity. And then as I go to the right from here, my slope goes negative, which means here on my derivative function, my y value goes negative. just a couple more questions here. So given the graph that we have on the right here, we want to answer these three questions. So suppose f of x is continuous for all real numbers. The image on the right shows the graph of the derivative function. So this is a derivative function. And so I'd like you to answer these questions based on this derivative function. Once you're done answering those, you can restart the video. So I'd say pause the video now, answer the three questions, restart to compare your answers with mine. Number 7, does the graph have any horizontal tangent lines? Well, since my derivative function has some y values of 0 here and there, that means that my original function had horizontal tangent lines where x is -2 and where x is +4. So x-intercepts on the derivative function are the x values or x coordinates where my original function has a horizontal tangent line. Therefore, we had horizontal tangent line at x equaling -2 and +4. Number 8, does the graph of my original function have any vertical tangent lines? And again, my answer is yes. The original function has a vertical tangent line where x equals 0 because the y values of this derivative function are both approaching infinity. So the y value is going to infinity, this y value is going to infinity, both positive infinities, which means my slope from the left was a positive number approaching vertical, and from the right, a positive number approaching vertical from the right as well. So a cusp would have had one side of my derivative function approaching negative infinity and the other approaching positive infinity. So again, as we look up here, where we had this cusp, one side goes to positive infinity, one side goes to negative infinity. On our previous page, we had this example here where we had the vertical tangent line and left and right sides were approaching positive infinity. Now, if instead our graph had curved more like this, if I had a negative to a vertical tangent line like that and then curved the other way, then my derivative function would have had the asymptote here and both sides would have gone to negative infinity because I have a negative slope approaching negative infinity, negative slope approaching negative infinity. So it's not always a positive infinity, but in this example it was, and it was also in question number 8. Question number 9. Does the graph of the original have any corners? And we want to explain. So here we say the function does have a corner where x is equal to 2 because the derivative function is undefined there and left and right hand limits are approaching different values. So here, since my left hand limit approaches this value, it's saying that the slope on my original function is approaching this positive number, but from the right side, it's approaching a smaller positive number. So both are positive, but the graph has different slopes. My original function will have different slopes because my derivative function has different y values at those two edges. So this means y equal f of x, the left-hand slope and the right-hand slope are approaching different values. So let's just think again a little bit about what this might look like at that point. So here, because I have a really steep positive slope, my original function so has a really steep positive slope, but my slope is going to decrease and become less positive. But then all of a sudden at this point, it switches. I kind of don't like what I drew there. I'm just going to back up a little bit, erase a little bit. There we go. So imagine my graph is coming down kind of like this. I have a, ooh, that's negative. It needs to be positive. No wonder I don't like my graph. Here we go. We had our infinite positive slope. So we had our vertical, and then it decreased, but still positive slope. And then all of a sudden, it becomes, at this point, a smaller positive. So it's a little bit hard to see, but there's going to be a bit of a sharp corner there as our graph switches from having this slope to having that slope just at this point. Not a great picture, but hopefully my explanation was enough to help you understand what's happening in question number 9 here. Oh, well, there we go. Long lesson. So time to stop the video, time to do some practice. All right, and we'll catch up again in our next lesson.